We've got two more example questions now for our curved lens problems. Example number 2 says an object located 32 centimeters in front of a lens forms an image on a screen 8 centimeters from the lens. That's an important statement right there. An image on a screen 8 centimeters from the lens. That's our image distance. The image is formed on a screen, but because it's formed on a screen, it must be a real image. Remember that virtual images can't be formed on a screen. Now, if it's a real image, the image distance is positive 8.0 centimeters. Sometimes it's positive, sometimes it's negative. If it's a real image, it's positive, and we know in this case that it's a real image because it's projected onto a screen. We want to determine the focal length of the lens and the attributes or the characteristics of the lens. So write down some givens now. We know that DO is 32 centimeters. We know that DI is positive 8 centimeters, both positive, right? DO is always positive. DI is positive in this case because it's a real image projected onto a screen. We're looking for the value of F. So using our lens equation, we'll say 1 over F is equal to 1 over DO plus 1 over DI. 1 over F is equal to 1 over 32 plus 1 over 8.0. Let's solve for F now using our calculators. Remember, we're going to use that little trick with our calculators. 1 over 32 is 32x to the minus 1, plus 1 over 8, or plus 8x to the minus 1. Now, that's not the value of F. That's 1 over F. We're going to press x to the minus 1 again to get the value of F. So we're going to say that F in this case is 6.4 centimeters. Now, because we get a positive value of F, it's just mathematically worked out to be positive, that tells us that we must have a converging lens. Converging or a convex lens. Remember that a positive focal length goes with a converging lens and a negative focal length goes with a diverging lens. Now, real, virtual, inverted, upside down, right side up, bigger, smaller, what is it? Well, we know that this is a real image. We know it's a real image. We already told that because the image is formed on a screen. If we look at our magnification equation here now, m is equal to negative di over do. It's hi over ho, but it's also negative di over do. I don't even need to put numbers in here. Negative di over negative do gives me negative something. If it's a negative magnification, that tells us that we have an image that is upside down, or it's inverted. And finally, if the value of di is smaller than the value of do, then the magnification must be a number that's less than 1. And if it's less than 1, then it must be a smaller image. So we've got an image here that is inverted, that's smaller, and is real. We know it's inverted because it's a negative magnification. It's smaller because the image is smaller than the object. You can see that right away from our givens. And finally, we know that it's a real image because it's formed on a screen. Now let's take a look at example number 3. This one says an object is placed 20 centimeters from a concave lens of focal length 30 centimeters. Watch this. Really watch this. A concave lens is a diverging lens. Remember, you always want to translate it into the words converging or diverging. Converging gives us a positive focal length. Diverging gives us a negative focal length. So we got to watch this, right? It's a diverging lens of focal length 32 centimeters, or technically, the focal length is negative 32 because it's diverging. You miss that negative, you get this all wrong. We want to find the image distance, the magnification, and the attributes or the characteristics of this image. We're going to say that DO is positive 20. Again, positive because it's always positive for us. We're going to say that F is negative 32. Again, watch that. It's a concave lens or a diverging lens, so it has to be a negative focal length. We want to find DI, and we want to find M, and then we want to find the characteristics or the attributes of this image. So let's use our lens equation again. 1 over F is equal to 1 over DO plus 1 over DI. 1 over negative 32 in this case is equal to 1 over 20 plus 1 over DI. Let's do our little trick with the calculator again. Let's say negative 32, x to the minus 1. That's 1 over negative 32. Now let's take the 1 over 20 over by subtracting. 1 over 20, or 20x to the minus 1. When I press enter, that gives me a value of negative 0.08. That's not di, that's 1 over di. So let's flip that over now. You're hitting x to the minus 1 to get the value of di. di works out to be negative 12.308. Negative 12.308 centimeters. We should have actually rounded that to 2 digits. But we have the unrounded number in case we need that for a calculation later on here. The fact that we have a negative di tells us that we have an image that is virtual. If you remember your ray diagrams from yesterday, you should know that it's a virtual image. When you have a diverging lens, it's always a virtual image. So if you thought back to your ray diagrams, you would know this. If you just looked at the sign of the answer that we got for di, you'd know that it's a virtual image as well. All right, let's calculate the magnification now. M is equal to negative di over do. That's negative 12.308 divided by do, which is 20. So let's say 12.3, it's positive because negative times a negative is positive, right? Divide that by 20 gives us a value of 0.62. The fact that that is a positive magnification tells me that the image is upright. Think back to the table. And the fact that it's a magnification that is less than 1 tells us that the image is smaller than the object. If we have a magnification that's greater than 1, the image is bigger. A magnification that's less than 1, the image is smaller. So we have an image distance of negative 12, a magnification of 0.62. The attributes are that it is a virtual image, it's an upright image, and it's a smaller image. And if you think back to your ray diagrams that we drew yesterday for concave or diverging lenses, this agrees nicely with that. All diverging lenses produce images that are virtual, upright, and smaller.